They've built a different kind of AI, and it may outgrow language models. What if the next leap in artificial intelligence didn't come from teaching machines to talk better, but from teaching them to understand better? That's the bet behind a new AI architecture unveiled by Meta, and it challenges one of the core assumptions behind today's most popular models. The system, known as VLJA, Vision Language Joint Embedding Predictive Architecture, takes a sharp turn away from large language models. Instead of obsessing over words and sentences, it focuses on something far more fundamental: meaning itself. Why today's vision language models hit a wall? Most vision language systems still think in fragments. They generate responses one token at a time, slowly assembling text like a puzzle. This process is not only sluggish, but also inefficient, especially in situations where speed matters, such as live video analysis or real-time interaction. There's another problem hiding beneath the surface. When a model concentrates on producing the right phrasing, it wastes effort learning stylistic details that don't actually improve understanding. You only find out what the system is trying to say after it finishes talking, which isn't ideal if you need instant insight. A shift from words to meaning. VLJA flips that approach on its head. Instead of predicting the next word, it predicts embeddings, mathematical representations that capture meaning directly. These embeddings live in a continuous semantic space, allowing the model to reason about concepts without getting tangled in language variations. By focusing on meaning rather than phrasing, the model learns faster, generalizes better, and avoids unnecessary complexity. Language becomes an output option, not the foundation of intelligence. How the VLJA system is structured. At its core, VLJA is cleanly designed, with each part serving a clear purpose. A visual encoder turns images or video into compact semantic representations. A predictor estimates meaning by combining visual input with textual queries. A Y encoder translates target answers into semantic embeddings. A lightweight Y decoder steps in only when readable text is needed, mainly during inference. This separation allows the system to stay focused on understanding, rather than constantly generating language. Where VLJA really shines, speed and efficiency. The biggest gains appear during inference. Because VLJA produces a stream of semantic embeddings instead of continuous text, it can decide when language is actually necessary. This technique, known as selective decoding, dramatically reduces computational cost and latency. For tasks like video processing, this makes a major difference. The model can track meaning across frames in real time without stopping to narrate every thought. Strong performance with far less data. Despite its relatively modest size, about 1.6 billion parameters trained on 2 billion samples, VLJA punches far above its weight. It outperforms well-known benchmarks such as CLIP and perception encoders that were trained on tens of billions of samples. After supervised fine-tuning, the enhanced version of the model behaves like a flexible generalist. In visual question-answering tasks across multiple datasets, it comes surprisingly close to much larger systems that rely on extensive training pipelines and task-specific tuning. A breakthrough in understanding cause and effect. One of the most compelling results comes from tests of physical causality. In experiments where the model had to infer which actions would transform one visual scene into another, VLJA reached an accuracy of 65.7%, a new high watermark. What makes this notable is not just the number, but who it beat. The model outperformed larger vision language systems and even advanced language-focused AI in these perception-heavy tasks. It is a strong signal that predicting latent meaning can outperform generating text when true understanding is required. Measuring the quality of understanding, further evaluation showed that VLJA's semantic space is unusually sharp and well-organized. Its embedding encoder detects subtle shifts in meaning more accurately than competing systems, indicating a deeper grasp of relationships between concepts. When researchers removed key stages of training, performance dropped sharply, especially in classification and retrieval, confirming that each component plays a critical role in building this semantic clarity. A new direction for AI, not a replacement. VLJA isn't trying to overthrow language models altogether. Instead, it points to a future where different kinds of intelligence coexist. Language models may remain essential for abstract reasoning, planning, and extended dialogue. But for perception-driven tasks, real-time video, embodied AI, environmental understanding, this meaning-first approach offers a faster, cleaner, and more scalable path forward. In many ways, VLJA suggests a quiet but profound shift. Intelligence doesn't have to speak fluently to think clearly. Sometimes understanding comes first, and words can wait.